Good day, everyone. So this video 100 subscribers. Thank you all. So this is the first integral video on the channel, and I would like to do this integral two ways. So two ways. The first way being the standard method using trigonometric substitution, and the second way being complex analysis. So let's take a look at the first way. So looking at this integral, we see that we have an x squared at the bottom or denominator, and it is x squared plus 1. And we need to recall, or maybe you already do, that tan squared theta plus 1 is equal to secant squared theta. Okay, so this is the substitution that we're going to use. We're going to say let x equal tan theta, which would imply that dx is equal to sec squared theta. That's from introductory calculus. And substituting this into our equation, we get, ignoring the limits for now, we have 1 over x is now tan square so this will be tan squared theta plus 1. Dx is secant squared theta d theta. Sorry, I forgot my d theta here. Now with the limits, as x goes to negative infinity, theta comes from negative pi over 2. So we have negative pi over 2 here. Because remember, the tan of 90 degrees is essentially tends to infinity, whereas we prefer to use radians than degrees in this case. And as x tends to infinity, we go to positive pi over 2. Now we could have left the limits for now and come back to it later, but this is also fine. And from this fact that we recall earlier, we see that tan squared theta plus 1 is equal to secant squared theta. So what we have is the integral from minus pi over 2 to pi over 2 of 1 over secant squared theta times secant squared theta d theta, and we can finally cancel this out. And we are left with the integral from negative pi over 2 to pi over 2 of just d theta, which happens to be theta, and we need to evaluate that from minus pi over 2 to pi over 2, which will be equal to pi over 2 minus negative pi over 2. Negative by negative is positive, so we just get this to be pi plus pi over 2 plus pi over 2, which is pi. So this is our first answer, that the integral from minus infinity to infinity of 1 over x squared plus 1 dx is equal to pi. Because if we look at the extreme right and left hand side of this equation, this is what we have. Okay, second method. Okay, so now we are going to look at the second method, which involves complex analysis. So we are told to evaluate the integral from minus infinity to infinity of 1 over x squared plus 1 dx. So I would like to start by considering the function f of z, where z is some variable, some complex variable, 1 over z squared plus 1. And we want to evaluate this on the contour C, which is equal to L union gamma. And now let us define what L union gamma is, or what L is and what gamma is. L is part of the contour that z is equal to x as on the interval minus r to r. Now, this is essentially the x-axis, and if we substitute z equal x into our f of x, our f of z, we just get back our integrand here. Okay. Gamma, however, would be a circular segment or a semicircle. Z is equal to r e to the I theta, where this is a circle with radius r centered at the origin. And this is on theta being 0 to pi, because we only consider in the upper half plane or the semicircle. So if we were to draw this, we have something like this, where this is minus r, this is r, this is my gamma, and this is L. L is going from minus r to r, and gamma is the semicircle that I'm only taking from 0 to pi with values of theta. Okay, so now f of z can be written as, well, it is z squared plus 1, which can be factorized as such, where I squared is equal to negative 1, sorry. So where I squared is negative, write this as I is equal to the square root of negative 1, but a lot more people is comfortable with I squared equal negative 1, because the square root of negative numbers doesn't make any sense to us. So we are on the verge of using Cauchy's residue theorem, and we should probably state what that is. That says the integral, well, the enclosed integral of any complex function is equal to 2 pi I times the sum of the residues of that function. Now, what is the residue of a function? That is just all the places where the function is not necessarily defined. As in this case, it has two poles, we call it, at z equal I, which will give this part being 0. And remember, we cannot divide by 0. And negative I, where this part goes to 0. And we also get a division by 0. So we have to calculate the residues at those points. However, we only have to calculate the residue at I, since we only consider the upper half plane. Negative I will be somewhere here, which is on the lower half plane, but we only consider the upper half plane. So the residue at this simple pole, this is a simple pole because it is only of the power 1, is given by, so I'll write the residue at I, is equal to the limit as z approaches I of z minus I times f of z. And what was f of z? F of z was 1 over z plus I by z minus I. And this is great because we could cancel off these things. And what we get is that the limit as z approaches I of 1 over z plus I, which is equal to, now we could just substitute z for I, well, I for z here now, and we'll get 1 over I plus I, which is equal to 1 over 2I. Lovely. So if we were to go back to this formula here, we can get a value for our integral. We have that the enclosed integral of our function is equal to 2 pi I times the sum of my residues, but I only have one residue, which is 1 over 2I, which is nicely cancelled. So 2 will cancel, the I will also cancel, and give me that the integral, which is the enclosed integral of f of z dz, is equal to pi, which is interesting because we haven't done any integral step yet, but what it seems like we have already gotten to the answer. but we are not ready to jump to any conclusions because this is analysis we are doing. So we have to do some further work on this. So the enclosed integral is really the integral from minus r to r. And remember, on the interval from minus r to r is f of z, f of z, which is z equal to x. So this is just f of x dx, because on this interval z is equal to x and dz is equal to dx. Plus the integral over gamma of f of z dz, and that should be equal to pi. Let's call this equation 1. And notice that if we take the limit of equation 1 as okay, we could probably not call this equation 1. Let's take the limit as r tends to infinity. As r tends to infinity, sorry, of our equation, we get, well, the integral from minus infinity to infinity, we can rewrite our x squared plus 1 here, dx, plus the limit as r tends to infinity of the integral over gamma of f of z dz. And if we take the limit as r tends to infinity of pi is just a constant, so it will remain pi. So let's consider this part. So we'll name this one 1, and we'll only consider this part here for now. So take the f of z. We said that that was equal to 1 over z squared plus 1. And on this interval, we have that z is equal to r e to the I theta. So it should imply that dz, taking the derivatives on both sides, is equal to I r e to the I theta. And then we still have this d theta here. And remember that theta is going from 0 to pi. Okay, so now we are ready to substitute. So we have the integral from 0 to pi, that's our limits, of r I r e to the I theta, that's d theta here. Now z squared will be r squared e to the 2I theta by laws of indices. So we have r squared e to the 2I theta, and then we still have this plus 1. Doing some further work, we can factor out an r from the numerator and an r from the denominator, r squared, sorry. So you will get r over r squared. Could have taken out the I as well, it doesn't matter. Integral from 0 to pi of e to the I theta divided by e to the 2I theta plus 1 over r squared d theta. Now, I know I may get some backlash for this, but for the sake of this video, we wouldn't go through the integral, but we can show that this is finite because the only variables that we have here is e to the I theta and e to the 2I theta, and these are finite valued on this interval. In fact, it is finite value on any interval. Right? If you take theta goes to infinity, it will become undefined, but it is strictly between minus 1 and 1, e to the I theta. So what we have is, well, I, because one of the r's will cancel. So we'll have I over r times some finite number here. And this is what gamma was, but we are taking, so therefore we are taking the limit as r tends to infinity of I times some finite thing over r. Now this on top is finite, and as we crank up r goes to infinity, this thing will approach 0. So we just shown that the integral or the limit as r tends to infinity of gamma of f of z dz is equal to 0. which would imply, so substituting this into 1, let's say that this is 2. So substituting 2 into 1, remember what we have the integral from minus infinity to infinity of 1 over x squared plus 1 dx plus our gamma term, which we just found out through some analysis was equal to 0. That is equal to pi, which would mean, because 0 plus anything is still that thing, the integral from minus infinity to infinity of 1 over x squared plus 1 dx is equal to pi, which we found out without using any integral. All we did was use analysis. So thank you for watching. I hope you all enjoyed this 100 subscriber video, and I will see you all in the next video. Thank you again for coming.